Suppose a model predicts hourly bicycle demand and looks excellent on a random test set. Random splitting mixes winter and summer, weekdays and weekends, earlier dates and later dates across both sides. If the real task is predicting future demand from past observations, the evaluation asks an easier and different question. It lets training include observations later than some test examples and gives both sets similar seasonal coverage. This is not always illegal. Random splits are appropriate for exchangeable observations. But time-indexed forecasting is not exchangeable in that way. The split must reflect when information becomes available. The cleanest leakage audit begins by defining the prediction moment. At this exact cutoff, which values exist, calendar features are known. A weather forecast may exist, but the realized weather recorded tomorrow does not. Yesterday's demand may be available, tomorrow's demand is the target. Even a feature named lag can leak if indexing was shifted incorrectly. Treat each feature as having both an event time and an availability time. The model may use it only when the availability time is no later than the prediction cutoff. This operational definition is stronger than asking whether a column looks suspicious. There are 3 common paths. Target leakage places a transformation of the answer into the input. A centered rolling average is a classic example because half its window comes from the future. Preprocessing leakage fits a scalar, imputer, encoder, or feature selector on the whole dataset before splitting. A pipeline fitted inside each training fold prevents that. Temporal leakage trains on observations later than the test row, or uses revised data that was not available at the time. Fixing it requires chronological data construction and timestamp-aware joins, not merely wrapping a scalar in a pipeline. A clear first protocol is a final chronological holdout. Sort examples by target time, train on the earlier block, and reserve the final period as the future. Fit every learned preprocessing step on the training block only. Report the calendar ranges because a hard final split may also create a difficult seasonal shift. That difficulty is part of the deployment problem if the model really must cross it. Compare random and chronological scores only as a diagnostic of protocol sensitivity. Do not select whichever score looks better. The honest estimate is the one aligned with how the system will encounter new data. Rolling origin evaluation strengthens the picture. Train on an early history, test on the next block, advance the cutoff, and repeat. Each fold respects the arrow of time. Expanding windows use all earlier data. Sliding windows restrict training to recent history when old regimes may be stale. Preprocessing and model fitting happen separately inside every fold. Report per fold metrics, date ranges, and failures, not only an average. The method cannot predict every future distribution shift, but it prevents an avoidable illusion, letting tomorrow help predict yesterday. A lower forward-only score is not bad news. It is the first estimate aimed at the real problem.